Hello, Science 20s. Hopefully for not too much longer, we'll be having these video chats and we'll all get back to class. But to start, where do we go in redox reactions now that we've been practicing them? Well, as you can see from my video, we're going to be talking about batteries and what exactly is this going to help us with. And so if you wanted to search up this TED Ed, and this is a new one that just came out, is talking about the world's largest batteries. But it's not your typical looking battery. However, for us today, we're going to be looking at the basic structures of what happens inside of batteries. First things first, before we jump into it, I wanted to talk about corrosion. We talked about metals and the redox reactions and we practiced with them last set of lessons. Now, I want to talk about what exactly is corrosion. Well, this is actually the oxidation of a metal, and so that's the loss of electrons. Therefore, these metal atoms are actually being converted into metal ions. And we're going to base this off of our activity series because we're going to have two different metals. And so one of these metals is going to go through an oxidation, and the other metal is actually going to go through a reduction when we have these typical battery cells that we're going to look at. To keep practicing with our activity series, please try these two questions. So pause it here and try these two questions. Now that we kind of reviewed a little bit of our activity series, we're going to look at this. This is called a voltaic cell. And so you see lots and lots of details going on here. Please take a moment and copy this into your notes. So what you see here, this is a voltaic cell, and this is going to be a spontaneous chemical reaction produced by a redox reaction. We have another different cell that we're going to talk about where it's non-spontaneous, but for today, this is only spontaneous cell reactions. What we see here is we have this cell and one side is going through oxidation. We see that right down here, and we're going to call this the anode. And then the other side we have down here, which is going through reduction, and it's going to be called the cathode. You might have heard of anode and cathode before, and remember from cations and anions, same idea, cats are positive. So there we go, cathode, anode, they're both electrodes in there. What we have is we're going to go through a redox reaction, and so we're going to have some reaction in here, and we're actually going to get a flow of electrons because remember, Leo loses electrons, goes through oxidation, and then here, going down into the copper, they gain electrons and they go through reduction. And then it completes it because then we have the flow of the salt bridge to have the ions flow back. What we're going to do is we're going to base it off of this table right here. You can see here, why does it happen this way? Well, when we highlight it, we have our copper right up here, and we have our zinc. I only cut it off a little bit, but we can see where we have our two metals. We have both the solids in there, we have both the ions in there. So which reaction happens? Well, I told you these voltaic cells are spontaneous. So for this to happen, we actually have to have the copper ions, and we're going to go towards the copper solid, and it's going to flow down this arrow to the zinc, and this zinc is going to go through the other way, and it's going to have the solid go this way, and it's going to turn into zinc ions, and then it follows the arrow back up, completing our circuit. So what we're actually going to see is our zinc metal, it's actually going to start corroding away because it's oxidizing, it's going to disappear. And what's going to happen on the copper is it's going to actually start building up because it's gaining, and it's actually going to start getting thicker and thicker, and it's going to pull the copper ions into the copper metal to make it more and more solid. So we see it all right here. This battery is just a set of a voltaic cell, and it's just joined together to provide this electric current or this flow of electrons. That's why we need this cell to be working. And that's kind of our end goal, is we have this reaction happening, and once the reaction is complete, there's no more flow of electrons, and that means the battery is no longer there. Our last little set of terms here, we are actually going to talk about the electrodes, and we see they're a solid electrical conductor which connects the cell to the external circuit. And so this would be the parts where we actually connect the battery on the ends. Or if you've ever seen the 9-volt battery where you have the two ends, you always have the positive and negative ends. And that's why it's so important to put batteries in the proper direction, because you need the flow of electrons going in the proper direction as well. Everything relies on going from that negative to positive, from A to C. And so we'll dive deeper into how do we solve other problems with these voltaic cells and how do we look at these redox reactions. First, as we dive into it, I want to talk about this thing called cell notation, because it's hard to draw out a full voltaic cell every time. So what you're going to see is here is a short and condensed version of what's actually happening in a cell. And so we see here, we had the zinc and we had the copper. We knew over here we went Leo. This was our losing electrons. And this is our anode. This is the way we always write it. We write our A first, our anode. And we saw, just like we saw the wire, the flow of electrons went this way. Our reaction was also that same way. And we can read it this direction. It was solid zinc loses electrons and it made the zinc ions. As it continued and we went on to the cathode, we saw this was the gain electron side. And the reaction can be read as a shorthand again, where we had our copper ions reacting. They gained electrons and they made copper solid. And so we can kind of just read it left to right, and it tells us the two reactions that are actually happening in a voltaic cell along this salt bridge to allow these ions to actually transfer, and then having our flow of electrons. And we're going to practice with this shorthand cell notation as well. But it's just a way to take out all those plus signs and arrows, and just a quick way to describe to people what's actually going on. So a few little memory tricks if we want to help with all this new terminology. So remember that a loss of electrons occurs at the anode, and that gain of electrons occurs at the cathode. Way we can remember this is Leo A and Ger C. And so we always can remember the Leo A and oxidation and anode are both vowels. Ger C and that reduction cathode, they're both consonants. So that's an easy way to pair them up. We have vowels and consonants. And we just remember where it happens, and this will help identify within the cell. Also remember that electrons flow in this voltaic cell from anode to cathode. So that flows from A to C. As long as we remember it's A to C, and anode or ano is negative. So anode is the negative, no. So just little memory tricks to help remember and put all these terms into practice, hopefully. And this is what it requires, is here's all these new terms, and we're just looking at it a little bit differently. Now we need to practice. So when we're given a problem just like this, first thing is, what the heck is happening? Our first dead giveaway is here. I don't have any kind of power source, and we're also working with only voltaic cells so far. So we know this is going to be a spontaneous reaction. So that means we're just going to follow our activity series, nothing too confusing. When we go from here, we need to be looking at our activity series as we're working through this. So again, we're going to see, how do we have this reaction become spontaneous? So first, I want to find my two metals. I have copper here. I have silver here. For this to occur, I need my reducing, or my strongest oxidizing agent, to be higher. So I need this one to go through reduction. I need this reaction to go through oxidation for this to happen. And so right away, this is already telling me what is happening. And now that I can find that one is higher, I need my silver ions to flow this way. I need them to gain these electrons and to go through reduction to become solid silver. I need my copper to to go this direction, I need it to lose these 2 electrons and keep flowing to make the ions, and then it goes up this direction and I get my flow of electrons. So what that means is my copper is oxidation. Okay? My silver is reduction. If we just remembered my memory devices, we had Leo A, so this is going to be my anode. C, so reduction, C is my cathode. And now I'm starting to label and piece it all together. If we remember, electrons flow from A to C in alphabetical order, so I can put my arrows in now, and I can see how my arrows are going to flow, and I can see what's happening with my reaction. And so identify the electrode where oxidation occurs, right here, my copper. There's A. Describe the oxidation process at the anode. Well, I can write it out as copper solid, right here. Copper solid reacts to lose 2 electrons to form my copper ion. On the other side, describe the reduction process at the cathode. Well, I read it just like here. I start here, go through reduction, and I have my silver ion plus my electrons reacts to form my silver metal solid. Okay. And then describe how the salt bridge completes the circuit. Well, we need these flow of ions to happen in here. These ions aren't changing anything, but we need this NO3 to flow. And we need this electron cycle to continue. So this KNO3 separates, and we have our neutral kind of spectator ions to help the transfer of ions throughout the whole circuit. And we can see right away, now we've identified the different species by looking at our activity series. So let's look at another question. Here we go. Here's just a blank slate. Here's a blank drawing. Ignore the pluses and minuses. But rather, let's not draw this cell out because it's much faster to actually draw out with cell notation. So use gold and iron. So instead of like drawing this all out, labeling gold and iron, and trying to draw our salt bridge and everything else, maybe we just want to figure out the anode and cathode and go from there. So let's jump in, forget the picture drawing, we just pull up our reaction series. And we need to identify gold up here, perfect. There's my gold reaction, and then there's my iron reaction. Remember, if it needs to be spontaneous, I need my strongest oxidizing agent at the top. And so that means right up here. This is my strongest one up here, gold. It's right at the top for us. So that means it needs to go this direction. It needs to go through a reduction reaction. And it'll flow, and we see my arrows flow down, all the way flowing down to iron, which we see here. This will be my stronger reducing agent, and this will go through oxidation. And we see that here, and then it flows and it follows the arrows up. And we get my 2 species. If we remember how to go through it, okay, reduction at the top. And if we remember C, reduction, okay, that's my cathode. Down at the bottom, this is going through oxidation because it's the opposite way it's all drawn. Remember, we have it up here. We're showing all the reduction reactions. If we go the opposite way, it's an oxidation. And so my losing electrons oxidation is my anode. And I want to start with my anode. And so my anode, and I read it just like here, my Fe, solid, I can put in the solid. Goes through oxidation to turn into Fe2+. And then I have my salt bridge, and I keep reading, and now I go through my reduction, which is Au3+, reacts, and it gains electrons to make solid gold. And I can put that there, solid. And there I showed my cell notation. Please make sure when we're going through it, oh, there we go, I even had it in there. Perfect. So when we're going through it, please make sure instead of just practicing with all these drawings and knowing how it flows, you need to know this way, you need to know how to read the activity series. In your workbooks, please practice pages 29 to 31. This is all dealing with voltaic cells having these spontaneous reactions and seeing where we were going with these redox reactions. Before we move on, we want to make sure we get this down really, really well. So take care and practice hard.